We're going to continue now with our discussion of how to draw molecular structures. This time, however, we're going to extend our discussion of how to draw simple Lewis structures into how to draw structures for some common organic molecules. What this will include is a discussion of common bonding patterns within organic molecules, how to recognize elements of unsaturation. This is a way of finding out from a molecular formula if a molecule has rings or double bonds, and then finally how to put that information together to draw a plausible structure for a common organic molecule. What we're going to talk about now is common bonding patterns within organic molecules. Now, what we mean by common bonding patterns here is, can we tell if we have a specific atom what the formal charge is going to be by only looking at how many bonds and how many dots that atom has? Now, I want to start by saying here that you can notice that the formal charge states that we're looking at range from -1 to +1. In organic chemistry, multiply charged atoms, so atoms with a +2 charge or a -2 charge, are extremely uncommon, and we'll call out any rare exceptions where that's the case. So what I'd like to be able to do here is I'd like to be able to take carbon, nitrogen, and oxygen and figure out how many bonds and how many dots each of these atoms will have for the most common charge states, -1, 0, and +1. As an example, let's take a look at the neutrally charged atoms. So to start here, I'm going to assume that our atoms all have filled octets because that's their most stable state. Now, one of these entries in the table will not be able to have a filled octet no matter how hard we try, and we'll talk about that a little bit later. So for example, if I take a look at carbon with a charge of 0, a neutral carbon atom, carbon is in group 4, meaning that in order to have 0 charge, the bonds and dots must sum up to equal 4. Now, there's a lot of possible ways to do this, right? So we could draw this carbon atom here with 4 unpaired electrons. That would be 4 dots and have 0 charge. We could have 3 dots and 1 bond. We could have 2 dots and 2 bonds. We could have 3 bonds and 1 dot, or we could have 4 bonds. Now, if we look at all these possibilities, most of these lack octets and so are a less plausible bonding pattern for a neutral carbon. It has to be this last one, as that's the only way that we can draw a carbon atom that has a neutral charge and a filled octet. So that's what goes in the box here, 4 bonds and 0 lone pairs. One thing I want to note before we move on is that even though I've drawn all of those as single bonds, they don't have to be single bonds. It just has to be a total of 4 bonds. So that means that a carbon will be neutral if it has 4 single bonds, or 2 double bonds, or a triple bond and a single bond. We can have any combination of those for that charge state. Similarly, we can use the same process to show that a neutral nitrogen atom will have 3 bonds and 1 lone pair, and that a neutral oxygen atom will have 2 bonds and 2 lone pairs, which we saw back in the previous video. Now, what I'd like you to do here is think about the other entries in this table. So go through and fill in each of the other entries in this table using the process that we've just seen. Remember that all but one of these has a satisfied octet. See if you can figure out which entry in the table is the one that lacks an octet. So go ahead and take a minute here, draw some atoms out, and see if you can't match their charge states. Unpause the video when we're done, and we'll discuss each entry in the table together. Alright, so let's go through the rest of this table. If we start here at a carbon, carbon with a -1 charge will always have 3 bonds and 1 lone pair. Nitrogen will have 2 bonds and 2 lone pairs, and an oxygen with a negative charge will have 1 bond and 3 lone pairs. For the positive charges, oxygen will have 3 bonds and 1 lone pair. Remember the hydronium ion from general chemistry? This is where we'll see these types of species the most frequently. Ammonium ions, so NH4+, nitrogen with 4 bonds and 0 lone pairs has a positive charge. And then finally, if we look at a carbon with a positive charge, we'll have 3 bonds and no lone pairs. So the item in the table that lacks an octet is the positively charged carbon. Carbon with a positive charge lacks an octet and is a very important species in some reactions, which we'll be discussing at some length later in the semester. All of the other entries in the table have satisfied octets, and that is the vast majority of cases that we're going to be seeing throughout the semester. If you want to extend your knowledge here, try to test it, try to fill out the table similarly with boron atoms and chlorine atoms as well. That'd be group 3 and group 7 respectively. We will be seeing boron-containing species several times throughout the semester, and halogens are very common, so it's good to be able to recognize those patterns as well. I can hear the question now, right? We've got all this work to filling out this table, but so what? How do we actually use this? Well, let's take a look at a common type of problem that we're going to see throughout the semester, which is we need to draw a structure from a molecular formula. So let's say I wanted to draw a structure of CH4NO-. Now, this particular molecule happens to have no double bonds, and we'll talk a little bit later about how we know that. But what I want to start with here is that one of the atoms in this molecule must have a negative charge in order for this to be possible, right? We have an overall negative charge. We have to assign a negative formal charge to an atom. So if I want to draw a structure for this molecule, what I can do is I can just throw down a skeleton for this molecule. Here I've used my 3 internal atoms to build a skeleton with carbon in the center and nitrogen and oxygen on the ends, and I can start by assigning that charge to one of the atoms. So the initial assumption I'm going to make is that let's say that charge is on the nitrogen. Well, I know from my common bonding pattern that in order for nitrogen to have a negative charge, it needs to have 2 bonds and 2 lone pairs, so I can fill that in. That means my carbon is neutral, so it gets 4 bonds, which I've shown here. Oxygen would also be neutral, which means it has 2 bonds and 2 lone pairs. And now the only thing I have left to do is fill in my hydrogens. Now, if I look at this molecule with my formal charge added, I check my atoms, right? So do I have a molecular formula of CH4NO-? Yes, I do. Have I exceeded the octet of any second period atom? No, I have not. Does my overall charge match my formal charge? Yes, it does. And do I have the right total number of electrons? If I double check that, I'll see that I do. So this is a valid Lewis structure for this molecule, which I've constructed without having to put too much thought into exactly what I need to do here. Now what I'd like you to do is practice this. Use this same process to assume that the charge is on the oxygen and that the charge is on the carbon, and see how that changes how you draw the Lewis structure. Assume we have the same skeleton, and assume there's no multiple bonds, but draw new structures by making those assumptions. Pause the video here, and then we'll check your work when you're done. All right, so if we start with the assumption that the negative charge is on the oxygen, we would end up with this structure here. You can see that both nitrogen and carbon have the common charge patterns for neutral atoms. Nitrogen has 3 bonds and 1 lone pair. Carbon has stayed with 4 bonds. Now our oxygen has 3 lone pairs and 1 bond, which gives it a negative formal charge. If we put the negative charge on the carbon, we end up with a structure that looks like this. Now, this is something that bears a little bit of note, which is that we have generated 3 different molecular structures that all contain the same atoms. If we have this, different molecules with the same atoms but different connectivity and therefore different structure, there's a term for this. These are known as constitutional isomers. Let's look at some examples of constitutional isomers. These 2 structures are examples of constitutional isomers because if we look at them, they both have all the same atoms, 4 carbons, 1 oxygen, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So they both have the same molecular formula, but they are connected in different ways. In the top molecule, the oxygen is connected to the end of the carbon chain. In the bottom molecule, it's connected to one of the central carbons. So this is an example of 2 molecules which are constitutional isomers. Same atoms, different arrangement. These 2 molecules here are actually not constitutional isomers. And the reason why they're not may take a moment to see because of the complexity of these structures. So why are these molecules not constitutional isomers? They both have the same molecular formula, but why are they not constitutional isomers? So the key here is to remember that the way we draw a molecule, the sketch that we make, is completely arbitrary and does not actually represent the real shape and size of these molecules, especially if we're just drawing a Lewis structure. So that means that we need to be able to check if we can manipulate these 2 molecules in some way to make them all line up perfectly. So I'm going to start by taking molecule B on the bottom, and I'm going to rotate it 180 degrees. I'm essentially going to flip it over, right? So here, this is still molecule B. I have not changed anything about the molecule. I've just turned it over and changed the way it's drawn. Then finally, I'm going to take these two groups here and swap them because the order in which we connect the atoms doesn't matter to get this, which is still molecule B. If we look at these two molecules, what we can see is that molecule A and molecule B are actually the same molecule. We have the same atoms connected in the same order, we've just drawn them in two different arbitrary orientations. We need to be very careful about this when we're checking to see if two molecules are the same or not, because it's very easy to accidentally draw a molecule twice, which could imply something incorrect about a reaction. Let's do a little bit of practice now in terms of both drawing Lewis structures and finding constitutional isomers. I'd like to know which of these two molecular formulas has more constitutional isomers, C3H8O or C3H9N. Now, some parameters for this problem is that neither of these molecules has rings or double bonds, and all of the atoms are neutral. There is zero formal charge in both. We're only looking for the isomers which have no formal charges. So go ahead and work on this problem and see how many isomers of each molecule you can draw, then we'll come back and answer the question. Okay, let's take a look at this. For C3H8O, here's one way in which we can build a skeleton for our molecule. We can attach all the molecules in a line with the oxygen in the middle. We could also attach all three carbons to each other with one of the oxygens as a branch, or we could connect all three of the carbons in line with the oxygen at the end. After we've done this, we can add the hydrogens, like so, and then we can add the lone pairs to be sure that all of our atoms are neutrally charged. Note that there is no way to draw a structure where carbon has both a filled octet and a lone pair, so the lone pairs have to be assigned to the oxygen in these cases. These are the only three constitutional isomers for C3H8O. There are no additional ones. If you drew molecules that look different than the three that I've drawn here, go through and check them. These are the only possible constitutional isomers, but I may have chosen a different arbitrary orientation for some of the atoms. You should be able to identify yours with one of these three. As for the other molecule, C3H9N, there are 4 constitutional isomers. Did you find all of them? If you found more than 4, check to see which ones are duplicates. So far I've told you that none of our molecules contain rings or double bonds, but how do we actually know that's the case? The way we do this is we look for what are known as elements of unsaturation. So to let you know what I mean by unsaturation, unsaturation basically indicates that a molecule either has a ring or a multiple bond, or a combination of both. So we'll start here by asking how many hydrogens could possibly fit in a molecule with 2 carbon atoms? What is the maximum number of hydrogens I could have? Well, in order to do this, I would draw 2 carbon atoms, I would give them enough bonds so they would both be neutral, and I would fill in hydrogens at every available bonding position. So if I have 2 carbons, I can fit 6 hydrogens. If I have 3 carbons, how many could I fit? Well, I have the structure here for propane, which has 3 carbons in it, and we can see that it fits 8 hydrogens. Now, we could keep going like this and draw 4 carbons and 5 carbons and 6 carbons, and we would soon see that a pattern would develop that if I have maxed out the number of hydrogen atoms that I can fit in a molecule, it will always have a molecular formula of the form CnH2n plus 2. That is to say that a molecule which is saturated with hydrogens, has the most possible, will always have 2 times the number of carbons plus 2 hydrogens. If instead I draw a 3-carbon molecule with a double bond or with a ring, I'll see that I can fit fewer hydrogens in. So 1 double bond or 1 ring will give me a molecular formula of C3H6. So this is what's meant by unsaturation. Each time we add a double bond or each time we add a ring, we have 2 fewer hydrogens than that maximum number we could possibly fit into a molecule given a number of carbons. Since there's a certain amount of mathematical uniformity to the formulas that we can write, we can come up with a mathematical equation to represent the elements of unsaturation, how many rings or double bonds we have in a given molecule based only on the molecular formula. So this is the formula that we're going to use here. 2 times the number of carbons plus 2, plus the number of nitrogens, minus the number of halogens, minus the number of hydrogens, divided by 2. Now, the reason why the formula works the way it does is going to be covered later in Organic 2. For now, we just need to be able to use this. Just as an example, let's say I have this molecular formula, C4H7NO, and I want to know if my Lewis structure should contain rings or double bonds. I can plug the number of each type of atom into my formula and come up with an answer. So for 4 carbons, 1 nitrogen, 7 hydrogens, and 0 halogens, I get that this molecule has 2 elements of unsaturation. So this means that I could have 2 double bonds, or I could have 1 triple bond, or I could have 1 ring and 1 double bond. So starting with these assumptions, we can draw Lewis structures which match this. So let's say I want to draw Lewis structures for each of these. I'm just going to draw some skeletons that would be plausible based on the calculation that I've just done. So here's a structure that could accommodate 2 double bonds and has no rings. Here's a structure that could accommodate a triple bond and has no rings. And here's a structure with a ring where I'm going to have to add a double bond in later. Moving along, we can draw our 2 double bonds in our first molecule. We can fill in a triple bond in our second molecule. And we can fill in our 1 double bond in the third molecule. Now note that all of these are working on their way towards being constitutional isomers. Since they all have the same molecular formula, changing the number of rings or double bonds means that all I'm going to do is be changing the connectivity, but not the number of atoms. In my first molecule, I can fill in sufficient positions for 7 hydrogens, matching my restrictions on charge, so none of these should have a formal charge. I can do the same thing with a molecule with a triple bond, and I can do the same thing with a molecule with a ring and a double bond. Therefore, drawing 3 molecules which are constitutional isomers, which all have a formula of C4H7NO and 2 elements of unsaturation. Now, when you're drawing Lewis structures, it's very, very important to not forget to obey the law. The law in organic chemistry is thou shalt not exceed the octet of a second period element. So molecules like this, where nitrogen has 10 electrons, are not acceptable. Don't do that. Don't draw a carbon with 5 bonds. No, don't do that. Stop that also. This is the law, and it shall not be violated. You can never exceed the octet of a second period element. It is, however, common for third period and above elements to frequently exceed their octets. We will very frequently see this with things like sulfuric and phosphoric acid. And just like in general chemistry, we're generally going to say that you favor the structure that minimizes formal charge. So for instance, this is a potential structure for phosphorus acid, H3PO3, but we would favor the structure that does not put formal charges on the oxygen and the phosphorus. By sharing a pair of electrons between oxygen and phosphorus, we can get an expanded octet species which has no overall formal charge. We will generally consider that to be better. Don't forget to go check in your general chemistry books for examples of this to see when and why we might want to do it. It's also important to point out here that the 2 structures that I've drawn are not constitutional isomers because they have the same skeleton, a central phosphorus connected to 3 oxygen atoms and 1 hydrogen with 2 hydrogen atoms on 2 of the terminal oxygens. These structures are resonance forms, which we'll cover in a later video.